Okay, so now we continue the lectures about defects in ionic crystals. And you, of course, realize that this will be similar to what we discussed earlier about the defects in semiconductors and metals. But the difference is now that because you have charge states of the atoms, then this will affect what kind of defects are likely to be in any way stable. Because if you have a electrically charged defect, it's unlikely to exist in large quantities, because then the entire crystal would be charged, and this would make the entire crystal unstable. So to put it simply, one can say that the defects must be one way or the other charge neutral to be reasonably stable. And then the other thing is that in ionic crystals, the anions are much bigger than the cations. So this means that anion interstitials are unlikely to exist, at least if you have a densely packed ionic material. Because of this, the simplest point defects are the vacancies and interstitials, of course, but the thing is that because the anions are large, negative ions are large, it's unlikely to have an anion interstitial. So you can have anion vacancies, cation vacancies, and cation interstitials, and the interstitials maybe in between the atoms or maybe in split positions like in the metals and semiconductors. But the thing is that since we want to require charge neutrality, these have to be somehow grouped or neutralized to become a charge neutral defect. And well, the obvious way of doing it is to do a Frenkel pair, take a cation vacancy like here, and then have a nearby cation interstitial, and then of course the charge remains neutral because the cation carries its charge with it here. Well, the other thing, which is almost as obvious, is to have a Schottky defect, that is, have a pair of vacancies, a cation and an anion vacancy, and in this case, because you are taking out both charge states, you also, of course, get a neutral defect. But here is now an important distinction that when you talk about a Schottky defect, if you talk about it in a non-ionic material, a Schottky defect means a single vacancy. If you talk about it an ionic crystal, it now means a pair of vacancies, so two missing atoms. So moreover, the obvious thing is then that, of course, that if you have a pair of cations and anions missing or extra in equal amounts, then you will be in a charge neutral state. And at the same time, these defects will preserve the stoichiometry. That is, you will still keep the same ratio, the cation to anion ratio, 1:1. But things are not quite this simple because there are also defect types which can lead to non-stoichiometric compounds. That is, that where the cation to anion ratio associated with the defect is not 1:1. And this is possible if the two elements have different charge states. So to make this clearer, if you take up iron oxide, well, there are many different iron oxides, but for now, for simplicity, let's discuss iron monooxide, monoiron monooxide. But iron in general can have two charge states, iron 2+ and iron 3+. So if you have normal stoichiometric iron oxide, then oxygen has the charge 2- and iron has the charge 2+. But if you have two iron 3+ atoms near to each other, then one can have an iron ion missing and one is still in a charge neutral state, because there are two extra pluses coming from these two iron 3+ atoms, and this can compensate for a missing iron 2+ vacancy. So to illustrate this point, so this means that you can have an iron 2+ vacancy and then have nearby two iron 3 plus atoms which are here and right next to the vacancy, and this way we still preserve charge neutrality. But obviously in this case stoichiometry is not preferred because we are missing one iron atom. The number of oxygen atoms is the same as before, so this thing is charge neutral. And in fact, in this case, what it means is that this iron oxide becomes iron deficient. And you can actually build up a fairly large concentrations of this kind of defect, and then you end up with a compound which is not monoiron monooxide, but is better denoted iron 1 minus X oxide, where this X is then some number close to 0, but still larger than 0. So this was a quick overview of the intrinsic defects in anionic materials. Of course, ionic materials can also have extrinsic defect, which means that you have impurities. And you can have any number of different impurities, but again, this requirements of charge means that it's if you have interstitial atoms, they will be relatively small atomic radii, so that they would fit into the crystal. And substitutional atoms are likely to be on sites with the same charge state, at least the same sign as themselves, because otherwise the local charge becomes too large. But if you have impurities with the same charge state and about the same size as the lattice atoms, then you can easily replace the original lattice atoms with this kind of impurities. And one can have substitutional impurity ions, which are roughly the same size as the original atom. In this case, a cation here, and in this case, an anion impurity, which is a bit larger than the other anions. And then interstitials can be there in between the cation interstitial impurities can be there if they are small enough to fit in. So to make this more concrete, if you look at sodium chloride, also known as regular salt, you can have a calcium and oxygen 2 plus and 2 minus impurities in ways that are charge neutral. So if you have if the initial geometry of sodium chloride is this, then you can have a calcium 2 plus impurity replacing 2 sodium plus ions, and then neutralized by having a vacancy here. So here you have a calcium 2 plus which has substituted for 1 sodium, and then you have a sodium vacancy, and this way this thing is charge neutral. And then similarly you can have an oxygen 2 minus replacing 2 chlorine ions, then you have the same charge state, and in this case the oxygen would be in an substitutional site, chlorine site, and there would be 1 chlorine anion vacancy. So this was sort of this simple atomic or ionic picture of defects. However, there is a different way of achieving charge neutrality, and that is to have electrons or holes that are bound to a defect. A hole means here a lack of an electron, a positive pseudoparticle, which is a standard quantity in solid state physics and semiconductor physics. So if you have an anion vacancy missing minus 1 charged ion here, the other way to neutralize it is to have an electron bound to the atoms around it. And this actually makes sense in the sense that now you have an effective positive charge. So if there is a source of an extra electron somewhere in the system, it's very natural that the extra electron would come here and bound to these positively charged ions, and it would form some sort of hybridized electron orbital between the sodium atoms, which is right next to the vacancy, and the end result is then charge neutrality. This is of course something which a very simple picture. Cations and anions and plus and minus ions does not explain this. You need to remember that electrons are in reality quantum mechanical objects, so you have this wave function of the electron which can be spread in actually quite non-trivial ways, which can then achieve this effect. And all of these defects can be described with the Kroger-Wink notation, which is basically the same as before, but now charge states may be included. So you have V stands for vacancy, and hole small h, and electron is an E. Cations are often denoted with big M for metal, and anions for X for something else, typically halides or oxygen, which form these anions. And then this subscript I describes still an interstitial, then M for cation lattice position, and X an anion lattice position. And then charges are, for some historic reason, a positive charge is denoted with a dot, and the negatives are with a dash. Of course, one can also use plus and minus, but historically this notation has been used a lot. And a perfect lattice is described with a 0. Well, the reason these ionic material impurities is actually the reason they are important is that they have a strong optical properties. They simply affect the color of the crystal if you have a transparent crystal. This effect on the optical properties, by the way, is also true in semiconductors. For instance, silicon is not transparent. Silicon looks like a metal, but it's transparent for infrared light. And in silicon, you can use infrared light to detect defects as color centers as well. But for the strong ionic material, most of them are in their pure state are transparent, but then you start adding impurities. These give color to the centers, and actually this was historically the first way they were studied based on the color, and because of this the simplest color center is called the F center, where F comes from the German word for color, Farbe. So a simple F center is an anion vacancy which has captured an electron. And already this very simple atomic scale defect can give a major macroscopic effect. That is, in calcium fluoride, the simple F center makes it violet. And it can actually be very beautifully violet, like this sphere of calcium fluoride in this picture. And there are many other varieties of these F centers. If you have Fn centers, it means many F centers, many vacancies next to each other diagonally. Fn plus, Fn minus, you specify the charge state, and then you can have a Fa, Fb, Fc, that is a cation impurity atom or element A, B, or C next to the F center. So for instance, F2 plus A center would be two F centers with a cation impurity and a charge state of +1. And there are many other centers, and these centers are named typically with capital letters, and this is still for historic reasons, and these names don't always make much sense, to be frank. For instance, an H center is a chlorine 2 minus ion on a lattice site, a V center is chlorine 2 minus ion on 2 lattice sites, and so on. And there is a large number of these letter notations, which typically has happened that they have been first detected experimentally without insight what's the atomic level defect is, and given some capital letter name, which then has stayed on. Nowadays, slowly people are starting to use the atomic notation to detect the defects instead of these, but quite often still runs across this kind of H center, V center, X center, and so on. But now some of them are known, and some of them are also known very well what the structure is and what the effect on the color is. So, for instance, if you have quartz is of course crystalline silicon dioxide. If you have aluminum impurities in quartz, they give it a smoky brown, light brownish color, and these stones are known as smoky quartz. And this is actually many jewels as sold as smoky quartz. So now you know that if you buy a jewel smoky quartz, it's actually silicon dioxide with aluminum impurities. Another even more beautiful example is if you have iron impurities in quartz. These make the quartz purple, very beautiful purple, and this is the jewel known as amethyst, which is a pretty valuable jewel, so sold in many jewelry shops. So in fact, almost all jewels and other precious stones are defined by the defects in them. But this is of course something now as a physicist you know this, but if you buy a valuable jewel to your girlfriend or boyfriend, you may not when you hand it over say, oh, look at this beautiful silicon dioxide with iron impurities. I think your boyfriend or girlfriend is much happier to hear that you bought an amethyst and not silicon dioxide with impurities in it. And here is still some examples of atomic structures of centers in potassium chloride, sodium impurity, and then an empty position with a negative extra charge is known as an Fa center. An M center is two adjacent F centers, two adjacent vacancies with an extra electron. An R center is three adjacent F center in a 1-1-1 plane of the crystal structure. So because of this, in this 1-1-1 plane, all atoms are actually negatively charged. The 1-1-1 planes go through these atoms here, and then if you plot this, you would have three negatively charged electrons in the in a negative 1-1-1 plane. But of course, the next plane would then be a positive plus plane of the cation layer, atom layer. So this thing is charge neutral. Well, and the reason of this is these are known is that this color comes, of course, from the fact that the different centers have different light absorption bands, and this can be measured relatively easily. You can measure simply with spectroscopy at which wavelengths you have absorption, and this defines then the centers. At each center will have a relatively narrow absorption band, and this means that they can be distinguished and at least their relative concentrations can be measured by measuring the relative strength of these peaks. And there are many of these known. So this is just a list of what's known in quartz. Iron can make quartz green, barium can make it brilliant, soda ash can make it flogging, manganese oxide can make it violet or blue, cobalt oxide blue, copper chloride red, sulfur iron oxide yellow to ruby amber, neodymium oxide makes it yellow, and this is what's used in sunglasses. And then selenium makes it ruby colored, and also gold chloride or tin oxide. So as you see, there are many examples of this, and you also notice that this is not the same as the amethyst. This is iron in a different position because than in amethysts. And also, if you look really at the atomic structure, quartz and silica, because of their big importance in many places, starting from glass and continuing to the semiconductor industry, defects in quartz has been studied a lot. And here is a little bit more scientific description of what known defects can exist in quartz. This is still a 2D schematic picture of quartz, but still you realize that there is many different things. There can be oxygen vacancies, there can be silanol groups with an extra hydrogen. You can have a oxide replaced with hydroxyl groups instead of the oxygen being bound to another silicon, and one can have pair of these hydroxyl groups. one can have what's known as a peroxy linkage, where you have an extra oxygen, sort of an oxygen impurity atom, but bound to a silicon and another oxygen. So these double oxygen atoms are called a peroxy linkage. You can also have a peroxy radical, where you have two oxygens, but where the oxygen is not bound to silicon. And then you can have substitutional impurities, like aluminum instead of silicon, and then neutralized by, for instance, a lithium plus ion. And you can have isoelectronic cations. Germanium, which has 4 outer electrons like silicon, can replace a silicon, and then you don't break the crystal structure necessarily at all. The bond angles would change a bit. And then one can have a so-called non-bridging oxygen, which means that you have two oxygens which are not bound to each other. In this 2D picture, it may look a little bit non-obvious why these wouldn't bond, but in 3D there are many different orientations these things can have, and in 3 dimensions it's sort of easier to understand that one can have different structures here and so on. Also, the reason these are important is that the regular gas is of course not pure silicon dioxide. It's silicon dioxide based, but has some other atoms in it, and these kind of what's shown here as impurities, then if the concentration is high, leads to the structural regular glass in window panes and other common materials. So this concludes this video on the defects in ionic materials, and next we'll discuss a sort of strange topic, that there can be defects in amorphous materials.